Guys, welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easier to understand. Today we're talking about ideal gases, still in the thermodynamics part of the subject, and problem statement reads, 3 kilograms of helium undergo an isothermal expansion. The helium has an initial pressure of 500 kilopascals and an initial volume of 4 meters cubed. The final volume of the helium is 5.2 meters cubed. We are to find the initial temperature of helium in Kelvin, find the final pressure of helium in kilopascals, find the work done by the system in kilojoules, and draw the process on a PV diagram with respect to initial isotherm. We also are given the ideal constant, the R constant for helium, already given in kilograms. So whenever we're using the ideal gas equation on this problem, we know we'll be using it on the PV equals MRT format, M for mass as opposed to N for number of moles. Drew two balloons to represent what's going on in this problem, because we're going from 4 meters cubed to 5.2. So let's go ahead and write down what we know about these guys. So V1, we know we have 4 meters cubed, and then V2, we have 5.2. And before we do any math whatsoever, we know that we need work, right? So this helium is going to require energy in the form of work to go from 4 and expand to 5.2. What else do we know? We know the mass of the system is 3 kilograms, and we can assume that no mass enters or leaves because nothing is said in that respect. And we also know the pressure, initial pressure, so P1 is 500 kilopascals. All right, brilliant. What else do we know? We know that this is a isothermal expansion, so there's no change in temperature whatsoever. So let's make sure we take note of that, because then that means that our T1, whatever it is, equals T2, right? Because the temperature does not change. Okay, so note that on the first state, we have two independent properties, right? Thermodynamic properties. We have the pressure and we have specific volume because we have volume and the mass. So state 1 is completely defined. So that means we can find our temperature for 1. With our temperature for 1, we're going to have the temperature for 2. And with that temperature, then we're also going to have state 2 completely defined because we're also going to have the specific volume, right? Because we can combine these two information here. So with that, we're going to have the two states completely defined, and then it's very easy for us to find whatever. So let's go ahead and find the temperature 1 and then solve for the second state. So PV equals MRT. So in this case, we're talking about state 1. So I'm putting 1 everywhere, and we're looking for our temperature 1. So we just need to do PV1 divided by the mass and R. We know that we have all this information, so we're going to put 500 here, the 4 here, the mass of 3, and R, which is given, and it's 2.077. Right? Unit-wise, quickly check. We have kilopascals meters cubed, so that's kilojoules right there. Then we have kilograms of the mass, and then we have the unit of kilojoules per kilograms Kelvin. So kilograms, kilojoules, and kilopascals with meters cubed. We're left with Kelvin. So our answer, our temperature T1 is going to be given in Kelvin. We're given in Kelvin. Then we get about 320.97. So let's go ahead and approximate that to 321 Kelvin. That's the answer to part A. Okay, but don't forget this is also T2, right? Because it's an isotherm. So therefore, let's put part A here. So then when we go to part B, and part B, if you recall, asks us for what's pressure P2. So what is P2? Then we can do the same thing, right? Because we know PV equals RT. But for state 2, it's going to be the same thing, but for temperature 2 and volume 2. So again, mass is still 3. The R is still 2077. The T, because the same as T1, we can go ahead and put 321 because we know that. And this is 5.2 meters cubed. Okay. Unit-wise, quickly, same thing as before. No units changed, but it's always good practice to do this. Kilojoules per kilograms Kelvin. This is Kelvin, and this is volume meters cubed. So kilograms, Kelvin, Kelvin. And then we have joules per meters cubed. That's going to give us Pascal, right? So our answer here is going to be in kilopascals. And we get out of this math about 384.64 kilopascals. Let's go ahead and approximate that to 364.6 kilopascals. Right, brilliant. So that's the answer for part B. Part C, what do you ask? What is the work done? Okay, so what is the work required or done required for the helium to go from state 1 to 2? We know that work is defined as the integral of the sum of all the P times dV. We also know this is isotherm, so we can sub in where we have pressure. We can sub in using the ideal gas equation. We can sub that in for mass R divided by V, okay, and dV. And then because, and the temperature, dV, and because the temperature is constant, R is a constant, and our mass is constant, they all come out of the integral, so we're going to have M R T over here of this, and then the integral is simply the natural log of V2 over V1. Right, we have all the information we need, so it's pretty much just go for it, right? Just plug in the values and ram the work. Okay, so we have the mass of 3 kilograms, R of 2077. We have the temperature isotherm to be 321, and then we have the natural log of 5.2 meters cubed per 4 meters cubed. Unit-wise, that goes away, and we're only be left with these 3 units here. So we can check that quickly. We have kilograms, we have kilojoules per kilograms per Kelvin, and Kelvin. So Kelvin, Kelvin, kilograms, kilograms. Our answer is going to be will be given in kilojoules. And that turns out to be 524.768 joules. So go ahead and do 524.8. Brilliant. Last step, part D. Draw the PV diagram with respect to the initial isotherm. Okay, so let's do that. So part D, we need to draw a PV diagram. So we're going to have pressure in kilopascals on the y-axis. So I'll have volume in meters cubed on the x-axis. And we have the 2 pressures already. We have the 2 volumes, so let's go ahead and put the volume. So it's 4, and then it becomes 5.2. And pressure-wise, we found out the 385-ish, and the other pressure, which is 500, our initial pressure. All right, and then we know that at 500, we are at 4, so this is where they meet, and then at 5.2 meters cubed, we are at, and that's where they meet. And then we can draw the isotherm, which is going to be something like this. And we know this isotherm is, what was the temperature felt? 321 Kelvin. So that's the isotherm for 321. And the process itself, we're expanding the helium, remember, so we're going from, let's do that in black. So we're going from this guy to this guy on the isotherm, because we don't have any change in temperature when we go from 1 to 2. And this is obviously our state 1, and then our state 2 after the expansion. So that is our PV diagram for this particular problem. If you have any questions, let me know. Remember that PES requires energy to be able to do to expand, right? So this is energy that needs to be supplied either in the form, no, it can be in the form of delta U because the temperature does not change. So this is heat that is going into our system. Okay, if you have any questions, let me know, and make sure to subscribe to the channel so you're always up to date with our videos and always looking into the newest content.